Hello, today I'm going to present Chapter 7, Section 2, Newton's Law of Universal Gravitation. As we may know, Earth and many of the other planets in our solar system travel in nearly circular orbits around the Sun, and as we know, a centripetal force must keep them in orbit. Newton made the realization that the centripetal force that keeps planets in orbit is the same as the one that pulls an object toward the ground. He defined gravitational force as the mutual force of attraction between particles of matter. Later on, Newton developed a thought experiment in which he proved that orbiting objects are in freefall. To do this, he considered a cannon sitting on a high mountaintop. And as we know, as the horizontal velocity of a cannon when launched increases, the distance it travels increases as well. So he concluded that if a cannon is launched at the right speed, it can enter the orbit around the Earth. Uh, Next, we will see a video in which Newton's thought experiment is thoroughly explained.
In fact, imagine a mountain 100 times taller than Everest. And imagine an enormous gun. It may not look far, but for such a tall mountain, this range would be very great indeed. Roughly, Land's End to John O'Groats. And this picture reminds us of an important fact. The surface of the Earth is actually curved, and we must take that into account as well. As a result, the shell will travel slightly further than if the Earth were flat. And now, the next stage. Imagine a gun that's even bigger. The shells fired by this gun will travel 10 times the speed of a rifle bullet. This time the range is really vast, roughly Birmingham to Moscow, and we haven't yet taken account of the Earth's curvature. With a shell of exactly the right speed, the path follows the curve of the Earth. And this is the result. Because there's no air that high, it doesn't slow down, and gravity pulls it all the time towards the center of the Earth. The shell has become a satellite. If gravity were switched off, it wouldn't stay in orbit. It would simply fly off into space. So a satellite orbits because of gravity, not because it's escaped from it.
Newton's law of universal gravitation. Newton later on developed an equation in which he described quantitatively the magnitude of the gravitational force. The equation is defined as gravitational force equals to the constant of universal gravitation times mass 1 times mass 2 divided by the distance between masses squared. In earlier times, the value of g was not known, but it was proven through experiments that the value was 6 times 673 times 10 to the negative 11th power, newtons times meters squared per kilogram squared. Gravitational force always attracts objects to one another. Also, gravitational force exists between any two masses, regardless of the size. For example, we see two desks in a classroom, and they have mutual attraction because of gravitational force. The force between the desks, however, is negligibly small relative to the force between each desk and the Earth because of the difference of mass. So now we're going to solve a problem involving gravitational force. Sample problem C. Find the distance between a 0.33 kilogram billiard ball and a 0.4 kilogram billiard ball. The magnitude of the gravitational force between them is 8.92 times 10 to the negative 11 newtons. We are given that the mass 1 equals 0.300 kilograms, mass 2 equals 0.400 kilograms, gravitational force equals 8.292 times 10 to the negative 11, and the constant of universal gravitation is 6.673 times 10 to the negative 11 newtons times meter squared over kilogram squared. So, we'll use the equation given at the beginning of the presentation, which is gravitational force equals to G times m1 m2 over r squared. We will rearrange the equation to find r, and we do this by finding the square root of G times m1 times m2 over f over gravitational force, which is equal to 6.673 times 10 to the negative 11 Newton times meter squared over kilogram squared times 1.35 times 10 to the ninth power. R is equal to the square root of 0.0898, and we find that R equals to 0.3, which is the same as saying 3 times 10 to the negative 1 meters. As we may know, gravitational force accounts for ocean tides. High and low tides are partly due to the gravitational force exerted on Earth by its moon. These tides result from the difference between the gravitational force at Earth's surface and Earth's center, depending on where the moon is. In 1978, a scientist known as Henry Cavendish conducted an experiment that determined the value of G, which was not known in the time Newton determined the law of universal gravitation. Although Newton discovered gravity, he was unable to explain every aspect of it, such as how it worked. For example, he did not know how every object created gravitational force without interaction. It was later discovered that gravity is a field force. A field force is a force that does not require contact to exert the force. Gravitational field strength equals to free fall acceleration. From Newton's second law, we find that acceleration equals to force divided by mass. And in this section, we find that the gravitational field strength equals to the force, gravitational force divided by mass. So we can say that acceleration due to gravity, or free fall acceleration, equals to the gravitational field strength. We have to be careful with these values because even though they are the same, well, equivalent, they're not the same. For instance, when you hang an object from a spring scale, you're measuring gravitational field strength, but you cannot measure the acceleration of an object at rest. So, in the chapter about forces, we learned that weight is the magnitude of the force due to gravity, which equals mass times free fall acceleration. We can now find out that weight is equals to the gravitational field strength times mass. These two equations or definitions are mathematically equivalent, but the new definition helps explain why weight changes with your location. Uh, we will use the equation of universal gravitation according with tennis ball and Earth. So we have the gravitational force equals to the constants of universal gravitation times the mass of the tennis ball times the mass of Earth over the distance between the two squared. So we combine it with the equation G equals to the gravitational force over m, and we get that G times the mass of Earth over r squared equals to the to G. So this shows that the gravitational field strength depends only on mass and distance. So therefore, the longer you get from Earth, the more distance between Earth and the object. In this case, the tennis ball, the lower the mass.